This is a summary on how to measure the characteristic time in the RC circuit using the oscilloscope as we saw it in the lab. You will see in the Notion webpage that you will receive in your Blackboard that at the beginning of each dataset, and there will be 3 datasets, there is a description of what happens in the capacitor and in the resistor as it charges and discharges. As we discussed during the lab, during the process of charging, the voltage can be modeled as V sub 0, visible maximum voltage, 1 minus E elevated to T, where T is the time, divided by RC. And we saw that this quantity RC has units of time. Therefore, this is later known as the characteristic time of the RC circuit. And we saw that when time is equal to this peculiar time, the voltage during the process of charging is equal to 63% of the maximum voltage, meaning that when the capacitor is charging at that specific time tau, the capacitor has charged 63% of its maximum voltage. During the process of this charging, the voltage can be described as the voltage across the capacitor can be described as the maximum voltage E to the T divided by RC. And at that characteristic time RC, the voltage across the capacitor while it is in the process of discharging, it's equal to V sub 0 e to the minus 1 when now the time is equal to tau. So that means that RC divided by RC cancels out and it simplifies to minus 1. It's equal to 37% of the maximum voltage, meaning that when the capacitor is discharging at time tau, the electric potential in the capacitor should be 37% of its maximum voltage. In the case of the resistor, in the process of charging, the voltage can be described as V sub 0 e to the minus t divided by RC, so that when time is equal to RC, the voltage should be across the resistor should be 37% of its maximum voltage at that characteristic time. During the process of discharging in the resistor, the voltage is equal to minus V sub 0 e elevated to T divided by RC, so that at that characteristic time, the voltage is approximately 37% of its maximum voltage. So that here we can see that the voltage in the resistor, when the voltage flips in the signal generator, we can see that the voltage is maximum when it flips. Then as time passes, the capacitor is charging, so that as the capacitor charges, the current across the RC circuit, it's diminishing, and as the current is decreasing, the voltage across the resistor is also decreasing, so that when the capacitor is completely full, there is no current across the RC circuit. Therefore, if there is no current, remember that in the resistor, voltage is equal to R, the resistance, multiplied by the current, so that if there is no current flowing across the resistor, therefore this is a constant, but if the current is 0, the voltage across the resistor will also be 0. Meaning that here, that means that if the voltage across the resistor is 0, there is no current across the resistor, therefore the capacitor is completely full here. Here, the signal generator flips, therefore the capacitor starts in the process of discharging and then charging in the opposite polarity. Here I'm going to describe using the data set 1 that you will see on the Notion webpage that I will send. In this case, remember that to measure that tau, which is the last part of the lab activity, to determine tau, theoretically, we can determine tau as equal to the multiplication of the resistance multiplied by the capacitor. In this case, you can see that the capacitor is here, and you can see that the knob is in this position. Therefore, the capacitance is 0.1, but remember the units, these units are microfarads. Therefore, for this case, I have a capacitor that is 0.1 microfarads. And remember that micro is 0.1 to 10 to the minus 6 farads. In the case of the resistor, for this case, it will be specified if this bottom is out or if it's in, because if it's out, you can see that you will have to use the low settings, which are in orange color. But if the bottom is in, that means that you will have to use the yellow setting, which is outside. In this case, the bottom was out. Therefore, if the bottom is out, you can see that the knob was in this direction. Therefore, the resistance is 470 ohms. For this case, therefore, we can calculate that characteristic time of the circuit tau, which is equal to RC, is going to be 47 ohms multiplied by 0.1 per 10 to the minus 6 farads, which gives us 4.7 per 10 to the minus 5 seconds. And remember that if we rotate the decimal point here, this will be to the minus 4, and if we rotate it again to the left, will be to the minus 3. Therefore, this can be written as 0.047 per 10 to the minus 3 seconds. And you'll see that this will be useful later because of the settings that the oscilloscope is. So therefore, if we can rewrite it as 0.047 milliseconds. And that is the theoretical characteristic time of the circuit. For each dataset, you will find that there are several measurements of the voltage across the resistor and of the voltage across the capacitor. I'll leave you to your discretion to determine which one is the best to make the measurement of the characteristic time. In this case, the figure that we see now is from dataset 1, and you will find it labeled in the webpage as figure 5. Below that figure, you will find the settings of that particular picture. If you see the label in figure 6, it says the vertical settings for figure 5. In this case, you can see figure 6 as this picture, where we can see that the vertical settings that we are using is channel 2, and you can see that the knob is actually in 1 volt, therefore meaning that each vertical box is 1 volt. In the case of the horizontal settings, you will find it on figure 7, which is the figure that we can see at our right. In this case, the knob says 0.2, and remember that the horizontal settings is, in this case, milliseconds. Therefore, each box in the horizontal axis is equivalent to 0.2. If we want to take a measurement of the characteristic time in this picture, you can see that we can do it because we can measure from here to here and throw a line to determine that, and you can see that it's almost here. But in the dataset, there is an isolated measurement that is easier to make this measurement. Figure 8 is actually an isolated measurement of the voltage across the resistor. And you can see the settings in the vertical axis in figure 9. And you can see that the vertical axis didn't change, so it stayed on 1 volt. And in figure 10, you can see that the horizontal axis also stayed the same. The only thing that actually changed is that I moved the voltage that I could see in the oscilloscope to the right so that I can have the ruler there and see the measurement in an easier way. During the lab, we discussed the best way to make this measurement. As a way to summarize what we said, is that the first step was actually to determine which was the maximum voltage. In the case of the resistor, the second step was that we knew that when time was, especially this characteristic time, the voltage across the resistor was going to be 0.37 of the maximum voltage. Therefore, if we find that maximum voltage, all we had to do was to multiply that maximum voltage by 0.37. And once we had that voltage, the third step was going to the graph and see where this voltage happened. Once we locate it, move in the horizontal direction until we see it on the oscilloscope, and then move on the vertical direction to see what time or to what time that does that correspond. And that time was actually going to be, or is going to be, the characteristic time of the circuit. For this measurement, we can see that the vertical axis corresponds to 1 volt per each division. Therefore, to determine the voltage, maximum voltage, all we have to say is my setting says 1 volt per division. And how many divisions do I have? Well, this is 1 division, 2 divisions, 3 divisions, but it doesn't go all the way up to 4 divisions. We can see that in each division there are 5 more subdivisions, and in this case it took 4 of the 5. So we can say that this is going to be 1, 2, 3 divisions plus 1, 2, 3, 4 of 5 divisions. That is to say, this is going to be 3 plus 4/5 divisions. Therefore, we can see that divisions and divisions cancel. At whatever that operation is, it will give us the voltage. In this case, we can transform this part as a fraction. Therefore, V sub 0 is going to be 1 voltage per division. And this is going to be 3 in terms of fifth, can be written as 15 divided by 5 plus 4/5 divisions. Therefore, this is V sub 0, which is equal to 1 volts per division. And 15 plus 4 is 19 over 5 divisions. Divisions cancel. Therefore, what we have is 15 divided by 5 is 3.8 multiplied by 1. So the voltage, maximum voltage, is 3.8 volts. We could have figured out this without necessarily involving this calculation, because if you knew that each division is 1 volt, in this case it's divided by 5, so each subdivision is going to be 0.2. So in this case it would have been 1, 2, 3. If each subdivision is 0.2, therefore 3.2, 3.4, 3.6, and 3.8. Once we have that, the second step is determine how much is the voltage when the time is the characteristic time. For that, we take this maximum voltage and we multiply it by 0.37. In this case, we can do that. Voltage in tau is going to be 0.37 of the maximum voltage, which is 3.8, that voltage. And it gives us 0.37 multiplied by 3.8 is 1.2. 1.406 volts. All we have to do now is go here and find where 1.4 volts happen. Well, this is 1, this is 1.2, 1.4 is here. So that means this is 1.4 volts. All I have to do is move in the horizontal direction. And now I know that this is the voltage of 1.4. Now move on the vertical direction, and you can see that this almost happened there. All we have to do now is determine that time. How do we determine that time? Well, the horizontal division says that each subdivision, each square, is going to be 0.2. So if this is 0.2 and this is 0, all we have to do is that the time is going to be the number of divisions. Now we have that this is 0.2 milliseconds per divisions, and we have to find how many divisions this is. You can see that this is not a whole division, so it's not 1. And we can see that we can represent these subdivisions as 1/5 of the whole division, 2/5 of the whole division, 3/5 of the whole division, and 4/5 of the whole division. In this case, since we have a picture and by eye we can almost see that it's in the middle of it, we can say that this is 1.5 of 5 divisions. This is 1, 2, 3, 4, 5, and this is 1.5 of 5 divisions. Divisions cancel, and this gives me a tau that is 0.2 per 1.5 divided by 5, which is 0.06 milliseconds. If we remember, now that we determined tau, we remember that the theoretical tau was 0.047 milliseconds. And you can see that these two numbers are quite close. Okay? If we can see that this is just to the second decimal place, and you can see that this to the second decimal place, if we round it up, it's almost 0.05 milliseconds. To do the measurement across the capacitor, there is a very useful trick to think of. During the discussion of the lab, we thought of the signal as being alternating between positive and negative signal of the signal generator. But let's think for a moment that that signal generator was actually between 0 and being positive, and 0 and being positive. In this sense, if I plot here, and I'm going to plot on top of this the behavior of the signal generator, I'm now, to make this measurement easier, going to think that this is a positive voltage and this was like turning it off or 0. This is positive and 0 and positive. In this way, I can see that the voltage across the capacitor, since at the end, what I'm interested in terms of voltage is the difference in the voltage. That's what we call voltage. The electric potential is the difference between the 2 points that we have. In this case, I'm thinking that this now behaves as a 0, and this is going to be the voltage that it charges. In that case, we can see that the vertical axis is still 1 volt, and I'm referring to the image on the left. It's still 1 volt. Therefore, I can say that this is 1, 2, 3, and it's almost 4, and it happens the same. So that means that that voltage, V sub 0, is approximately 3.8 volts. In this case, the way that I'm thinking this, not now as a oscillating voltage between like AC, between a positive voltage and negative voltage, but now thinking of it as just 0 voltage, and now it turns on the voltage. Now this process will completely represent a charging process, and this other voltage will represent a discharging process. A charging process and a discharging process. This is very useful when we are talking about just DC current. If we want to make the measurement across the capacitor, we can see and we remember that this is now our 0 and that the maximum voltage was 3.8 volts. But we must remember that the behavior of the capacitor during the process of discharge, I'm referring discharge, let's call it capacitor when it's discharging. The voltage in the capacitor at that specific time is going to be 0.37 of the maximum voltage. But in the capacitor when it's charging, the voltage in the capacitor when it's charging at that time tau is 0.63% of the maximum voltage. In this case, the measurement that I have isolated is a process of discharge. Therefore, if I am talking about discharge, I can then use this relation. That means that during that process of discharge, the voltage across the capacitor at that time tau, I can find it as 0.37 of the maximum voltage, which is 3.8 volts, and that gives me 0.37 per 3.8, it's 1.406 volts. And 1.4 volts, I can find it since the vertical divisions are in digits of 1. That means that this is 1. Now this is 1.2, 1.4. And I can see that this is 1.4 volts. I go in the horizontal direction. I cross the path of the voltage in the capacitor. And now I move in the vertical direction. I see that I have almost the same result as the last measurement in the resistor, because now each horizontal division is still 0.2. That means that the whole square is 0.2. But I have this is divided in 5 sections, so this is 1/5, 2/5, 3/5, 4/5, 5/5, which is just 1. So this is approximately 1.5 of 5 divisions. Therefore, to find that characteristic time, I can say that tau is going to be my base divisions, but my time divisions is 0.2, 0.2 milliseconds per divisions, and I have a 1.5 divided by 5 divisions, divisions, and divisions cancels out, and 0.2 multiplied by 1.5 divided by 5 gives me 0.06 milliseconds. I'll leave you to your discretion, because if you have a measurement where you can see the process of charging, therefore, in that case, remember that first you find out the maximum voltage. Once you find out the maximum voltage, in the case of charging, that is not the case that you are seeing here, it will be the voltage of 63% of the maximum voltage. You go to the graph, you find the 63%. Then once you find it, go in the horizontal direction and find the time where that voltage happens. And the time when the voltage is 63% of the maximum voltage during the process of charging will represent tau, which for these settings should be almost the same. I hope this summary was useful. And remember that although here I discussed the two ways, the resistor and the capacitor, you can decide to do that measurement in either of them. I am not requesting you to do both. In that case, the important part is that once you determine tau and you have your theoretical tau, you can find a percentage error, which is defined as the difference between the experimental tau that you find out minus the theoretical tau divided by the theoretical tau multiplied by 100. And what this is giving you is how far is your experimental result from the theoretical result. And I hope that this was useful.